Hello, this video is going to focus on work done. Let's get started. Examination guidelines says that we should define work done as the product of the applied force on an object and the displacement in the direction of the force. This direction is going to be very important. Work is also a scalar quantity. By definition, that means it's a physical quantity that has magnitude only. We're expected to use this formula: work done is equal to the applied force multiplied by the displacement and the cost between the motion and the force. We also have to explain that no work is done when a force acts at right angles to the direction of motion. We need to be sure about our free body diagrams. We also need to introduce the concept of net work, which we'll see adding these subscripts of net to the force as well as the work. Then we have to define energy as the ability to do work and emphasize that both work and energy have the same SI unit, which is capital J for joules. So let's get started. We are first going to look at the formula. Now, when we look at the formula, work done is equal to force multiplied by displacement multiplied by cos theta. Now let's look at what are the possibilities within this formula. So if we talk about force, can we calculate the work done of any force? Yes, we can. So we can calculate the work done by the applied force, the normal force, the gravitational force, and the frictional force in most instances. It can also be tension. Say, for example, the applied force is the tension of a cable, pulling a lift upwards. The next part is this displacement. This displacement is how far did the object move? How far? And you need to locate that in the question, and it will most likely be given to you in meters, which is small m. Then now, this is the part that we need to tackle, the cos theta. Because I'm saying that let's take it as a rule that this cos theta only has three options: either 0 degrees, 180 degrees, or 90. And if we start with this 90 and you punch it into your calculator, you will see that the answer you get is 0. That means 0 joules of work is done at right angles. And what must be at right angles? The motion and the direction of motion and the forces, which can be in both of these directions because both of them are 90. Now let's look at the other examples. Cos 0, now let's look at the cos theta. So we've already identified that 0 work is done here. So we need to look at the 0 degrees and the 180 degrees. When are we going to use 0 degrees? We are going to use 0 degrees when the direction of motion and the direction of force are the same. So it means that if the object is moving to the right, the force must also be to the right. If the object is moving to the left, the force must also be to the left. Only that force that's to the left is the one that is going to utilize this 0. 180 on the other hand is, say for example, the object is moving to the right and the force we're talking about is moving in the opposite direction. So this will most likely be friction in the horizontal platform. And you can see that there's 180 degrees from that angles on a straight line. Another situation is, say for example, in the mall you take the lift. The lift will have an applied force that is lifting it up from the motor. What is acting opposite to that? It is going to be the weight, the gravitational force of the people inside the lift. So also in this situation, it is 180 degrees because the force you're talking about is this force, and it is acting 180 degrees to the direction because the direction is upwards. Here it is when you are calculating for friction, because friction is 180 degrees opposite to the motion. So you need to watch out and pay attention to which theta are you going to use. Now let's look at these three examples because you know I'm a scenario-based teacher. So in diagram A, we are saying that this box, 100 Newton force is applied to move an object. So this is going to be the applied force of 100 Newton. It also has a normal force always and gravitational force. It doesn't mention anything about friction, but let's say it is on a frictionless surface, then you'll also have friction in the opposite direction. Diagram B is saying that here you've got this box. Box has normal force and gravitational force always. If it's on a surface with friction, then it will have friction in the opposite direction to motion. And the only difference now is that the applied force of 100 Newton is acting at an angle. Diagram C is saying an upward force is applied to lift a 15 kg object of height 5 meters at a constant speed. So this free body diagram has its applied force lifting it up, and it will have gravitational force, which is going to be m times g, and we have mass and we know what g is equal to calculate the gravitational force. So now let's check what the questions could potentially be or possibly be and what we must do. Let's say, for example, in this diagram A, the question is to calculate the work done by the applied force. They can also say to move the box. In diagram B, let's say it's also to calculate the work done by the applied force. So we'll make this for A and B. And then also here in C, it is to calculate the work done by the applied force. So here it's going to be W is equal to force times displacement times cos theta. Is the applied force in the same direction as motion? Yes, so it's going to be cos 0. Is the displacement or the direction of motion and the force in the same direction? Yes, so it's going to be cos 0. Is the applied force in the direction of motion in the same direction? Yes, so it's going to be cos 0. So here it's simply going to be 100 moved 5 meters times cos 0, and that is going to give me 500 joules. I'm done. In this scenario now, we have to include the horizontal component here because every single force must move with its angle. So it's going to be the same formula, but this F is F cos theta. So it's going to be 100 cos 30 is the F. How far? 5 meters. Is it in the same direction? Yes. So it's going to be cos 0. And then you have to punch that into your calculator. And then you will get 433, 2 decimal places, 0.01 joules. Here again, we are calculating the applied force, but the applied force is not given necessarily here. But the application or the method will be exactly the same. Because it's moving in the same direction, we'll substitute the FA. It's moving 5 cos 0, and then whatever the force is given in the question, we'll substitute there. So that is using cos 0. When will we use cos 180? When will we use cos 180? We will use cos 180 when it is given in the opposite direction to the direction of motion. So if we have to calculate the work done of Fg here, we'll use 180. So work done by gravitational force in scenario 3 is going to be Fg, it's still moving 5, and then cos 180. Where are you going to get the Fg? You're going to say Fg is equal to m times g, which is 15 times 9.8, and that is 147 Newton. So you can substitute that in now. 147, 5 meters, cos 180, and your answer must be negative because this negative is showing that it's working against the system. In this situation, you will use 180 for frictional force and also here for friction because it is acting 180 degrees in comparison to the direction of motion, and that sums up work done.